Hi again. This is the second half of the video lesson on using the equations for constant acceleration. So what you'll want to do is probably have the problems out. Um, and you also want to make sure that you have your green sheet out that lists the kinematics equations. So if you haven't watched the first video where I derived these equations, then stop now and watch that video. Otherwise, let's go ahead and do this. Now, I'm going to just do one problem here, so this will be pretty short. But what is the strategy that we're going to use? The strategy is we're going to read the word problem, and we're going to try to identify all the pieces of given information. Usually, you're going to be given 3 pieces of information. Okay? And then usually you have to find the 4th. So you're going to play a game of elimination here, and you're going to basically figure out what you're given and what you have to find, and you pick the equation that has the check marks in those boxes, and then you just use it. Okay? It's actually pretty I don't want to say it's a no-brainer, but if you follow the steps here, you actually don't have to think too deeply about the physics. I don't normally like to say that, but that's kind of how these work. Okay. So I'm going to go ahead and go right to problem number 3, okay, because I think that one's the most interesting one on the first page, and I'll just do that one. All right, so let's read it. It says a car travels east with an initial velocity of 10 meters per second. Mr. Foley steps on the brakes, decelerating his vehicle at a constant 1 meter per second squared. How far will the driver have traveled in the first 5 seconds after having first applied his brakes? Okay, so the first thing we have to do is decode the words. And we're going to go through our list here, and we're going to figure out what we're given, what we have to find, and what is irrelevant. So I'm going to read again. The car travels east with an initial velocity of 10 meters per second. All right, that's pretty blatant, right? It's telling us an initial velocity is going to be plus 10 meters per second. I'll make it plus because east on a map is to the right, so that's standard. Mr. Foley steps on the brakes, decelerating his vehicle at a constant 1 meter per second squared. Okay, so constant is important. That signals that it's okay for us to use our equations on our green sheet. And then the 1 meter per second squared is clearly an acceleration. I'm going to write that here. But I have to also read between the lines here because it says he's decelerating. Now, decelerating basically means that if my velocity is positive, right, which we kind of assumed here, that my acceleration is going to have to be in the opposite direction. Okay? Has to be. So I need to make this negative. And I have to use my judgment to do that because it doesn't tell me -1. I have to actually think about it and maybe make a little sketch here that reminds me that when these things are opposite, that happens. All right, the next question, how far will the driver have traveled in the first 5 seconds? So it's looking like 5 seconds is my time. And when they ask how far, I think that that's really kind of asking about displacement. It looks like Foley is only going in one direction, and so we're really just trying to find his delta x, his displacement in that direction. So this problem is a problem that does not involve final velocity at all. I'm going to put an x through there because I just don't care about it, and I don't even know what it is. So my job now is to find one of the equations that links these 4 things, but not final velocity. And so if I look on my sheet, I can see, I hope, that this equation here, number 4 does the job, okay? Because it thinks I need to find displacement, I know the acceleration, I know the initial velocity, I know the time, I don't care about final velocity. So I can simply write that down here. Delta x equals v initial t plus 1/2 at squared. And I'm good to go. Now, we don't need to rearrange this because it's already rearranged, but sometimes you do, and I would like you to rearrange the formulas in this homework. So in this case, no rearrangement is needed. I'm going to copy the equation down. And then I'm going to substitute, and I'm going to be really careful with my values. I also like to put units in just because if the units don't cancel, I know I've done something wrong in my formula. So notice I put a negative in here for acceleration. Also notice I need to square the time. This is something students forget to do. So I'm squaring it here. I'm not squaring it here. Okay. And this is an interesting problem too, because in this problem Foley was moving initially. So he's going to have some initial displacement. Sorry. That's going to be found by VI times t. And then he's going to have more displacement because of his acceleration. So let's see what happens. So 10 times 5 gives me plus 50 meters. Okay, seconds cancel. I hope you can see that, it's kind of like if Foley was just driving at a constant velocity and he didn't do anything else, he would go 50 meters, right? Because 10 times 5 gives you 50. So that's actually part of our solution, is calculating how far would he go if he didn't accelerate at all. Okay. Now we have to also kind of modify that by adding in this other term, right? So over here I've got 1/2 times -1 times 5 squared. Now 5 squared is 25 times -1 is -25, and half of that is minus 12.5. Now this sometimes bothers students because they're like, well, what does that mean? And in the way that the physics works here is the fact that Foley is slowing down means that we have to kind of take something away from the 50 meters that he otherwise would have gone. So this 1/2 AT squared that we had talked about in the previous video, it comes in as a negative value, and you take it away from 50. And that is the way that you do this. It's kind of neat the way that you can break up the two displacements separately and combine them just by subtracting them. So at the end of the day, Foley has actually gone, what would this be, 37.5 meters. And that's because we took 50 and we had to take away from it some of that 12.5. So it's quite interesting that, the way that you solve this problem. Question for you, what if instead of decelerating at 1 meter per second squared, what if he actually hit the gas and he accelerated starting at 10 meters per second? Answer is that you'd still have the 50 meters that you'd start with, but then you would have to add 12.5 meters. And so his displacement would actually be 62.5 meters. And that should make sense because if he's accelerating in the same direction that he was initially traveling, he should be going further. Okay, so we're going to call that our answer for this problem. I would then invite you to go ahead and do a bunch more. These get more challenging as you go, but it's the same approach for each one. And I think the challenges that you'll find here are probably in using the right plus and minus signs. And in a few cases, you're going to have to use a quadratic equation to solve for t. You can kind of see that might be part of this equation here. Okay. So have fun with those, and we'll check in later.